Hello, everyone. Thank you for joining us today for AIAA Los Angeles Las Vegas section Saturday section E meeting. So today we have very exciting talk about the computer simulation with very hot topic, sustainable aviation. I know the couple expert is in our audience as well. So, we'll have a very interesting conversation toward the end of the presentation. So you can, interact with the speaker and see if there's some great insight you get. We can get from today's great discussion and meeting. So before that, we have a couple logistics to go over. We'll go very fast, and but while we are waiting for people to join us Saturday morning gradually, so it take a couple minutes. The purpose is to get people to sign in, and also this is AIAA Los Angeles Las Vegas section event. So we're going to, of course, to show some membership information. So first of all, today's talk, we are in the introduction. So in a couple of minutes, our speaker, Dr. Swati Saxena, will start her presentation. Then we'll have Q&A. And you are welcome to type your question in the Q&A box, but we highly welcome you click raise hand and speak out toward the end of presentation. So first of all, thanks a lot to the AIAA headquarters for this wonderful Zoom platform and all the support for all our activities. And thanks a lot to Dr. Swati Saxena for the recording permission. And if you have bandwidth issue, you can use dial-in for the audio and just use internet for the video. Again, if any question, type in the Q&A box and chat box for networking. But highly encourage you click raise hand more toward the end of presentation, and we look for a very exciting discussion. And first of all, AIAA is a wonderful organization, emerged from two distinguished organizations, one formed by the Wright brothers on aviation, the other formed by Robert Goddard, rocketry, both established in 1920s, and they merged in the early 1960s, become AIAA. So AIAA is not national, but also international. Our president right now is Mr. Basil Hassan, executive director, Mr. Daniel Dunbacher. Our section chair right now is Dr. Jeffrey Purcell of Raytheon. Of course, AIAA is nonprofit membership-based organization. Membership is a very important aspect. Is the core of the organization. And you can see we have so many, countries with our members, and we have corporate members as well. For example, Blue Origin, SpaceX, they are all corporate members, which is very important. You're welcome to encourage your company, organization to contact AIAA for corporate membership. Some individual might be covered because corporate, but it's not everyone, corporate. There are a lot of advantages joining professional society, networking, advancement of levels. It's great for your resume and publish, your work. AIAA publish and research. And this is just some of our exciting, volunteers. For Sherry from JPL, Dr. Pushel, Courtney from Boeing, Jennifer as an aerospace attorney, and RP from Glendale Community School. We have more and wonderful members just to show you how wonderful our people are. And these are different level of membership. Take a look, and if any question, contact us, and we'll be able to help you out, or you can contact customer service, aiaa.org/contact. Then you'll get everything done right away. By PAD, you got a lot of benefit, Aerospace America, conference discount, and networking. And one very important thing is the membership advancement for, member, senior member, associate fellow, honorary fellow. You can see that our Dr. Jeffrey Purcell is a fellow, and also Dr. Marty Bradley, as expert in a leader in sustainable aviation, is also AIAA fellow, leading this effort in sustainable aviation. and after Miss Queen Shotwell, Mr. Dr. Bill Gerstenmeyer, and also Dr. Mark Louise, our speaker on February 19, 2 weeks from today. He is our honorary fellow and also former one of the former AIAA executive directors. Thank you so much. And there are honors, and you can apply, get awarded, student membership, conferences, and the local Los Angeles Las Vegas section is blessed with vibrant aerospace activities from Boeing, SpaceX, Northrop Grumman. You can see the famous, very successful James Webb Space Telescope just launched Christmas Day, and Convergent Orbit Aerospace Corporation, JPL, or student activities. So many of them, and you have like electric hybrids, aircraft, sustainable aviation, several company. There's a very big one in Hawthorne, and a new company like Launcher Space, Relativity Space, and many others. And we have been doing events, for example, as I mentioned, 2 weeks from today, Dr. Mark Louise, and February 23rd, we have aerospace cybersecurity by Mr. Scott Nieber. He's director of cyber engineering aerospace corporation. And we have newsletter opportunities, and also we post our videos, a presentation video on YouTube and podcast. And we are so honored and so happy to have our speaker today, Dr. Swati Saxena. She is a lifetime senior member, very loyal member of AIAA, is doing wonderful job and doing in this field. She got a master degree and PhD in aerospace engineering from Penn State University. She led the research. She was also the lead research scientist and program manager in GE Global Research. She is a technical project manager at ANSYS, and she has been working on a very exciting area of machine learning, simulation, engineering design, model-based system engineering, PIDO, fluid mechanics, and aeroacoustic gas turbine design. She has been giving a couple of very exciting presentation with us. She is holding 20 plus publication and 2 patents. So it's really our great pleasure to have Dr. Saxena give this wonderful presentation today. So thank you so much, Dr. Swati Saxena again. So please, it's all yours. Go ahead.
Thank you so much. Thank you so much, Ken, and thank you for joining us this morning. Let me start. Okay. I think you have to. Okay, now I can share. Let me start sharing my screen here. Do you see it fine?
Yes, very good.
Okay, awesome. Thank you again for joining, and Ken, thank you so much for the great introduction. So today I'm going to talk to you about some of the simulation technology that we have been working on at ANSYS to help companies, industry, specifically aviation industry, reach their sustainability goals in the next 2 or 3 decades. So today, I'll touch upon the ANSYS simulation technology stack to begin with, just to give you an idea of the breadth of simulation portfolio that is available with ANSYS. And then we'll first look at the targets that aviation industry has put forth for us to achieve in next 3 decades until 2050 to get to net zero emission. And then the different technologies that are being looked at, they are at different TRL level, technology readiness level at this point, and how simulation can help accelerate those design decisions and help us get to these to mature these sustainability related technologies in a accelerated fashion. So we look at through simulation examples and how they can support the sustainability efforts. This is, of course, a very broad area, and a variety of topics could have been could be related to sustainability as far as simulation is concerned. So I'll touch upon few key areas today. There is much more, but we'll just, because of the time constraint, we'll look at few key examples. And if you have any follow-up questions, or need more information, please feel free to reach out to me after the talk. Okay, so for those who are not very familiar with ANSYS and the simulation portfolio that ANSYS has, let me give you a quick summary before we go into the use cases. So ANSYS has a very strong, high fidelity physics-based simulation software, going from structures to fluids, electronics, semiconductor, optical, so sensor design, camera simulation, and so on, and even 3D design and photonics. So it's a wide breadth of physics that ANSYS covers with its high fidelity software. Now, these are very useful when you are working on a detailed design or analysis, or you're looking at even maintenance side of these components in detail. But as we are now designing these next generation products, we are looking at component level, but we also want to see how that component would behave and perform when integrated in a system or a system of systems. So with ANSYS system level simulation tools, we have that capability of integrating this high fidelity component level physics into system level analysis, and then take a step further with system of system simulation with mission engineering. So we with the STK systems toolkit, the entire mission can be simulated in a simulation environment, along with and it can be coupled with the system level design as well as component level. So all these three levels can be simulated together in using different ANSYS tools. And of course, we can link with other non-ANSYS commercial and government and open source tools as well to achieve this ecosystem. This entire framework is supported by platform. So when I say platform, uh, these simulations have to be scaled on and run multiple times, and sometimes they consume a lot of HPC. So they can be deployed on cloud with commercial and both private cloud infrastructure. This process and can be deployed on a platform level tool like ANSYS Minerva, and it can link with the commercial product lifecycle management tools that are out there as well. So if we look at this entire journey, we are going from single physics to multiple physics or multi-physics, and then we can build a digital prototype in a sense where it can also consume information that's coming from the live asset or live product that's out there in the field. So this gives you the entire breadth of the simulation capability, going from component level to the mission level, and so that you can analyze and evaluate our designs much faster, and you can also expand the design space. So with that background, let's look at some of the uh, bigger engineering or product challenges that we are facing today to achieve these sustainability goals. And this is a bit generic here. It can be outside aviation industry as well, but these the high level objectives that industry is looking to achieve here remains the same. So we would like to reduce or uh, minimize the carbon footprint, and it could be coming from a variety of sources. So we have to minimize the greenhouse gas emissions. Energy, we have to look at the sources of energy, how are they being energy is being generated, how it's being consumed, and if there is a better way or a more efficient way to even transport it from one place to another. Materials is a big is an important uh, factor here, because that contributes to the carbon footprint as well. There are environmental and just human well-being factors which are also part of sustainability, because we will be looking at the level of, for example, water pollution or the noise or water usage in making these products, the level of acoustics, so level of noise that's being generated. So all those contribute to the environmental effects. The second pillar here is on the performance of the product itself. So if how energy efficient is the product, what's its current carbon footprint and how we can reduce it, what is the product life cycle, how does it look like, how is it going to be scrapped once it's done with with its life, how it's the facility where it was manufactured, how sustainable is that facility. Operational efficiency, so predictive maintenance is a key aspect right now. Traditionally, products when the products were in operation, there was a certain guideline that was provided for its maintenance, but then after that it was not tailored according to the environment that the product is going to function in. If the product is going to be in operating in a very harsh environment and very cold climatic conditions versus in a desert kind of very hot, harsh with a lot of dust, air a particulate in the air, that kind of atmosphere, it was not tailored around that, and the product parts can fail at a unexpectedly or a much higher rate than expected, or what has been it has been designed for. And that's where predictive maintenance comes into picture, and with the concept of digital twin and enhancing it with physics based models can uh, provide a much better estimate of how that particular product is going to perform in that particular environment, and then the maintenance can be uh, scheduled accordingly. Manufacturing sites, as I mentioned before, where the product is going to be manufactured, how efficient is that, can we make that carbon neutral, how can we make it more sustainable and safe. The time and cost is the third key objective that we need to focus on here as we are doing this technology development. How are we focusing on incremental changes, or are we focusing on some revolutionary technology that will take some more time to mature, but it will get us make us reach our aviation 2050 goals in a much more better way. Compliance is of course very important, and in the aviation industry it's even more important to meet all the regulations and standards before we certify anything that can fly. So with keeping this bigger objective in mind, uh, how simulation can help. So if we look at, these are just three examples, where simulation has helped reach the goals and faster, and the benefits can really be quantified, because at the end of the day we would like to see what is the value that's coming out. So if we look at emission, we are we are working on designs that are that will have reduced carbon emission. energy, reduction in energy consumption. Material, the material that is that has less environmental impact, and if that is chosen in a much more um, intelligent way or efficient way in the beginning on the design cycle of the product, then it will have much more uh, m- better design as well as less impact on the environment. And there's just three examples. I do have also have links here which you can visit to get more information about these, how they were achieved. But this is where the simulation has helped for these three particular products to achieve their goals, and we were able to quantify on how much they were able to save with the final design. Okay, so let's look at the aviation specific goals now. We looked at the overall objective, and that is valid for um, broader at the broader industry level outside aviation as well. And this is what you might have seen come up last year from the IA TA organization, where where they have put forth the targets for 2050, and they have also estimated how much growth there will be in carbon emission if we don't do anything. The passenger, the aircraft, journey, passenger growth is going to increase by several folds by 2050 in next 30 years. And if we don't do anything and we just continue with the current technology, this is where we land. This is where we are right now, and the target here is to get to net zero emission by 2050. And you see, this is a very big target, because we do not only have to bring it down from the current level, we have to really bring it down from the projected level. And this cannot be achieved by a single action from the industry or the prime integrators. It has to be a combination of several technologies as well as operations and infrastructure. So it has basically, they have broken it down into four categories: technology, operations, infrastructure, and sustainable air fuels, SAFs. So these are different ways through which they are going to tackle this objective here. And we can contribute to it in several ways through doing incremental changes in our current technology, looking at some revolutionary designs as well, and so on. So if we look further into these four aspects of um, operations, new technologies, SAFs, and just by offsetting carbon capture. So this is the kind of the percentage division that has been proposed, or has been that have come up with. As you see, this the biggest portion here is going to come from sustainable aviation fuels. So this is a very important area of research right now, how we can just use alternate fuels, or look at even biofuels, hydrogen, and other sustainable air fuel methods to reduce the carbon emissions and contribute to this net zero carbon 2050 goal. So in terms of the aircraft technologies, there are, and we all know about these different kind of technologies. They are, some of them are not even new. They have been studied for several decades now. Uh, but in terms of how we can, we can categorize them in terms of evolutionary and revolutionary technologies. Something that has been is more mature and would need some incremental changes to implement and try out, and others where we would be looking at um, more revolutionary designs or bigger changes in the aircraft design and operation itself. So advanced turbofan engine, that's something that we have been looking at, and it can contribute to uh, carbon reduction. Open rotor engine, that design has been looked at. GE had did some studies a couple of decades ago on open rotor design. It's the noise is high levels of noise is a constraint there, and now with new advanced materials, and also um, advancement in design as well, that's it's something that is being revisited. Blended wing body aircraft and another technology that has been looked at. um, the hybrid laminar flow. So just by reducing the flow separation, or and going to drag reduction, will help us make it more efficient, make the aircraft more efficient. New engine core concepts. So if we are just looking at improving the individual components in a gas turbine engine, that's something that is currently being looked at as well. Hybrid, and then the different kinds of the propulsion systems, hybrid electric aircraft and fully electric aircraft. Of course, several companies have been working on these designs. um, Several big um, companies have also made investments, have funded a lot of startups in this area, and we are seeing some good progress in coming up with these viable solutions in near future. So we will first look into some of the examples where the design work and technology evaluation work can be accelerated with simulation. As you know, I mean, these concepts are sometimes very expensive to test, and also when you are working with your design space, you have to first narrow down to a reasonable number of samples, which then you will have a physical prototype and do further testing before maturing the technology readiness level. So in the early design phase, even starting from the requirements, that's how early you can actually bring in the simulation and make decisions faster and in a more informed fashion. It doesn't have to be a high fidelity component level analysis where suppose you even don't have a CAD, you don't have a full-fledged geometry, still you can use simulation to come up with uh, make decisions at the system level, at the simplified design level with some discovery tools and so on. So this is just this is a busy slide, but it gives a summary of a variety of uh, areas where simulation can be used to predict the efficiency of the design that is being evaluated and the effectiveness. So starting from propulsion system, and it could be a different kinds of propulsion systems that could be modeled and tested. Rotor dynamics, and that's also a key aspect with these new designs, because you need to understand if there is going to be any fluid structural interaction, avionics, cooling, battery design itself, battery management system. These are very traditional applications with icing de-icing systems. It's there in current designs as well. These are uh, rotor strut interaction, so installation effects. When the rotor is installed, you can look at how it's going to interact with the structure, and whether that would create any additional sources of noise, for example, or any vibrations or um, fluid structure interactions that you have to consider. The HVAC system modeling is that this can be integrated into a system level modeling as well, and being looked at variety of configurations. The system design, control design, itself, aeroelasticity is with these blended wing aircrafts and the newer designs, we are going to have higher aspect ratio as well. Aeroelasticity becomes important and can be uh, studied. Acoustics, of course, noise is a key aspect, and uh, that is a very difficult physics that we has to be resolved in a very accurate fashion to get any accurate value out of it. The motor design with motor thermal management as well. Now with when we are evaluating these different kinds of propulsion systems become important, and if these motors have to be optimized and designed for the overall aircraft to meet the overall aircraft requirements. So different electrification scenarios can be modeled, right? So when you have, for example, this is just a schematic for a parallel hybrid propulsion system. So you have your battery, it's going to operate the motor, and you're going to have a turbofan as well. So you have to you need to model this entire system in different regions of the flight envelope. So this entire envelope can be simulated in the system level analysis tool, where you are not only mimicking the overall coupled propulsion powertrain, but you are also um, changing the operating scenarios during the entire envelope. Okay. Now, looking into a bit at a deeper level into the system. So here you see a schematic of the propulsion system itself. This is the uh, the aircraft engine components is simulated in a schematic manner, and the electric machine design and analysis as well, going from the component level to the system level integration. And also going back to component level for battery modeling and thermal management. So this will give you a detailed analysis of how the thermal profile of the battery looks like during charging and discharging and so on. Sorry. So we can look at the different aspects of the system, the system simulation level with, and we can also link it to the field data here. So this is the ANSYS Twin Builder platform, and it can build. So here you can build different kinds of propulsion systems that you are evaluating. So this is example of parallel hybrid electric propulsion system model. And this is, if you just zoom in into the electric system, this is how it looks like. So you see that it's just a box here, and it can expand. You can build a subsystem here. So if you expand this, you can see the entire subsystem. This can be linked to other system level analysis tools for the entire um, environmental control systems or other systems that you are planning to model, but this gives you a framework for incorporating these tools. And what I'd also like to highlight here is, for example, if you see a high pressure turbine here, and you have a inlet and outlet with temperature, pressure, and all other operating parameters specified, and you can specify a performance curve for this turbine. Now that performance curve can be derived from the overall specifications of the machine, or it can also be generated from a high fidelity analysis that you have done is done separately with a CFD solver, for example. So that can directly plug into the system level model. And what that gives you the flexibility of tweaking your design and modifying that performance curve according to your new design. So you are not just relying on the curve that you have from the original design, but on in a uh, incremental or like real time fashion, you are able to change that design, that performance curve based on the analysis you have done. And you can also create a reduced order model or a surrogate model for that HPT, and that can be plugged into the system level analysis. That gives you a additional level of fidelity there. So this just shows a study that was, and this is a representative study that was done to um, study the effect of the location of the electric machine in the entire system, and how its efficiency will change as a function of SFN, so the speed of the fan. So let me just play it one more time. You can, sorry. Okay, so you're increasing the speed, reducing the size, and that's the effect can be captured in this efficiency graph. And it can be, this is just one output that I'm showing here. There are a lot of other things that you can extract from this kind of simulation. This is another scenario, increasing the size of the fan, and also the overall location and dimensions of your motor that is installed there, and you can study its effect. So this is the concept exploration phase. uh, you can do it in a much more efficient way by automating most of this process. And there are tools like OptiSlang that can be linked to either our CFD solver or mechanical solver, and can run this study for you in an automated fashion. And you can parameterize where the geometry parameters like the radial length here, axial length, and also the different variables can be parameterized in terms of the flow speed, the fan speed, uh, the inlet pressure, temperature, and so on. So all those can be parameterized and run in an automated fashion. And the post processing can also give you things like response surfaces and response curves, which will help you identify those the areas where you would like to investigate further, and which are meeting the design requirements. So you can generate plots like this. This is the specific fuel consumption plotted against specific thrust, and you can see the minimum on this curve for different installed configurations. You can see where different components are included, and this uninstalled SFC, and install the all rack components included. It will give you a range of how each component is contributing, and uh, then you will you can make your decision accordingly based on the information that you get from these kind of studies. The different level of different component masses plotted against specific thrust, and the total mass of the engine. So a variety of information can be extracted and post processed with these response surfaces and response curves. Okay, so moving on to few specific examples. So this is the previous one I wanted to give you an idea of what kind of design exploration studies you can do on different kinds of uh, propulsion designs that you are looking at. We look into now some specific variety of use cases. This can be uh, related to different kinds of sustainability efforts across different physics. So the first one is around how we can reduce emissions with electric aircraft, and Again, with when we are working on electric aircraft design, we are looking at a variety of changes that need to be made to the aircraft. Of course, we are familiar with the objectives here. Will be reducing the carbon emission. There is a specific goal that we have in mind for these electric aircraft designs with electric motors. So the electric motor design simulation, the NVH simulation for the electric motor, the noise simulation, the for the rotor itself, the how these 3D flow field with interact with the structure, with the aircraft structure for fluid structural interaction. All those aspects need to be understood before we go to the physical prototyping and then testing, because again these testing these aspects can be very expensive. And if we are able to down select few important configurations beforehand, that helps us eliminate both risk reduction, that helps us with risk reduction and also cost optimization. So this is a specific example where the multi-physics environment was used to design the electric motor, right? So this is a MagniX example. But what I want to highlight here is, as I was mentioning before about the multi-physics aspect of design, when we are looking at the motor design itself, we can consider different physics in a single simulation. So the integrated approach gives you a better uh, visibility into your design space, as well as you can do multi-objective optimization in a single simulation environment. So this is the framework that was used for designing the motor in this case, and it was able to capture the both the fluids, structural and electromagnetic. So these three physics in an integrated fashion to give you a optimal solution where you will meet all the three kind of design aspects of the system. This is another example for designing a all-electric airplane. And here we are looking at the battery thermal management and how we can optimize it. So this study was done by using adjoint methodology. And what it does is, with the adjoint simulation, you are able to come up with a design where you have an objective in mind, and then you use the adjoint methodology to uh, come up with a design that will meet that objective. So for example, you want to modify the design, and there are several constraints that you can set as well. An example is to, for example, if you want to change the design of this wing, the airfoil design at a particular for to meet a particular objective, which could be a 10% reduction in drag. Now with that, you have other constraints as well. You want to still want to have a certain amount of lift, you want to have uh, a certain amount of thickness, a minimum amount of thickness for your airfoil at a certain location. So with all these constraints, you can run that optimization study in an automated fashion using the adjoint method to come up with the optimized design. So this is just an example of how this can be used to optimize certain portions or certain uh, features on the aircraft to meet the new requirements. Okay, so going from the design aspect of things, let's look at the into more detail about the fuel itself, and that is something that is currently being actively being investigated, and a lot of effort is being put in for studying different kinds of fuels. So hydrogen propulsion is big, and people are studying different aspects of the entire the feasibility of using hydrogen for the for as the primary fuel, and coming from starting from its extraction to storage to its combustion properties itself, and how much efficiency we'll be able to have. So different, again, different aspects need to be investigated and studied for this combustion design. So if you look at the combustion itself to start with, we would like to understand. So there are few objectives, and it's important to see what what our existing engine architectures can do. If we can use pure hydrogen or hydrogen blended fuels with our current engines, because that will save us a lot of time and help us get to the next stage quicker. uh, how we can support new hydrogen content, high hydrogen content combustion designs. Then what would be the NOx emission characteristics? So this is all of this needs to be understood in detail before we decide on using a certain kind of fuel. So this is the combustion analysis is again a very complex physics-based phenomena that needs to be modeled. Different fuel chemistry models need to be implemented, which were not traditionally used with the traditional aviation fuel. And then we have to go through a lot of validation, uh, given given our current the database that we have for current engines, and how that compares with the numerical models that we are using for these combustion designs. So the uh, ANSYS Fluent is being used for studying these combustion mechanisms. Different fuel chemistry is being implemented, and it's already being used at several by several engine manufacturers to make do these kind of calculations. Uh, the important thing here is to note that we for these high fidelity combustion simulations we need very accurate and improved like turbulence models as well. And that has been a primary focus, along with uh, making it automated uh, process as much as possible, because these meshes are also very large. They are as you can see this example, 100 million poly hex core mesh. It was generated in 20 minutes. So something that analyst or a designer can do on its own, and with limited amount of effort in spent in generating these meshes for even for very complex geometries. So not only automated, but run it or generate it in a parallel fashion, so that it can be it shouldn't take days to generate these kind of meshes. So that's where the effort is being put in. And then on the speed of the CFD of the flow solver itself, because these simulations take time. There is a lot of several equations that have to be solved simultaneously to capture the fuel chemistry, and it is very computationally extensive. So how we can scale it on cloud or your on-prem HPC infrastructure, so that you are able to run these simulations in a timely manner. It's not taking you weeks but days to get the results. Okay, I think this one is not working, but uh, believe I have a couple of animations later. We'll see some flame simulations. So this is a snapshot of the hydrogen cycle analysis that was put together in Flownex. So this is one of the system level simulation tools we partner with, and you can see the different components being uh, simulated here. represented for the hydrogen cycle analysis, and then the different parameters that can be set. So the reason that I'm showing here this schematic here is when we look at the combustor, we can link it to the high fidelity solution that is coming from ANSYS Fluent, and then use that as an input for your system level analysis, so that it will give you a better representation of your cycle, and for design exploration as well. The same optimization or automation workflow that I was talking about for the design side can be used for this propulsion cycle as well. So you have the hydrogen uh, cycle, propulsion cycle schematic. It can be parameterized depending on your design space, and then it can be linked to a variety of tools for doing the process integration and design optimization analysis. So this gives you an example of what we were talking in the beginning, where you are coupling your component level information to system of systems. So this is just an example for the hydrogen propulsion system. Now this is another example of a high fidelity simulation that is important here. When you have uh, hydrogen as fuel, you like to see if there is going to be a flashback. And this is the section that is being simulated here. And you have a high fidelity or a very fine mesh to resolve this phenomena. So probe locations, so these are uh, virtual probes that are being set when you are simulating, when you're running the simulation to see if you are going to have flashback. And you can see in this case, if you focus on this region, you can see that you are having some flashback in the hydrogen case as compared to CH4. So these are again very high fidelity runs, and the fuel chemistry and the grid resolution and the overall um, turbulence model is, all of those are very important to capture these phenomena in an accurate fashion. Okay, so now the other aspect of using hydrogen is the hydrogen aspect, hydrogen storage. And here what we are focusing on is the tank or the vessel that is going to be used to store hydrogen, and the material that it can be made out of. It has to be with all the constraints on the weight and of course structural integrity. This is the workflow that can be set up in ANSYS Workbench for a composite hydrogen storage analysis, vehicle design or analysis. And there, the key aspect that I would like to highlight is the composite um, material creation itself with ACP. The thermal analysis, you want to look at uh, the temperature or the thermal profile of the vessel, also its structural integrity, how much pressure, or if there are any key hot areas that we would like to be aware of which could be uh, damaged. And then linking it to the material management library, because here the material is being evaluated and the properties need to be very accurate and consistent material properties, and those can all be stored in a material management platform. And then like I've mentioned about OptusLang before as well, and this which can be used for this design optimization um, simulation setup. So we just looked through the solution, right? We are combining all these four portions of the solution to come up with the overall design. And then, of course, our constraints or objectives that are objective functions that we'll implement would be the weight and the structural um, integrity criteria. And so we look at the failure analysis and so on and make sure it's meeting all the criteria that we would like for the vessel. So this is a example of designing a pump for hydrogen propulsion system. So this is the snapshot of the workflow, with again in ANSYS Workbench for design for this pump design and analysis. And it could be for any generic application as well. It doesn't have to be for hydrogen pump. In this case, you would like to focus on that. And uh, this just tells you the series of steps that can be taken to do this design work. So we start with the requirements. That's the first step. Then we come into preliminary design tools. So that will be your mean line design, or uh, just like the 1D design that you'll be looking at. The 2D design, then it goes to 2D design. You'll be looking at the blade profile. Then there are different tools that can be used to generate the blade design itself, the 3D design, and then you do the high fidelity analysis on it. So here you are doing both fluid analysis as well as a structural analysis, so CFD and structural, to make sure you're meeting both those criteria. And this is the performance curve you are getting out of the CFD runs, and it was compared with test data from a NASA hydrogen pump as well. The entire process was automated in Optislang, and this just shows you a framework of how these components can be designed. Again, this is not just limited to pump; it could be implemented for any rotating uh, uh, component design. The fuel cell design, that's another example we can look at. And the different aspects of flow within the fuel cell can be modeled. And this was a fuel cell stack was modeled and analyzed in Fluent. And you can look at we can look at more details in this reference as well. uh, Inbuilt, there are some inbuilt CFD modules that are available. uh, and it can be, again, Fluent is highly scalable. So if you have very large stack models, they can be modeled as well. Meshing is a key aspect, because you would like to be able to model these complex fuel cell geometries accurately, and then extract different kind of information from it. So this again uses the some of the inbuilt models and chemistry that's available for the accurate modeling for fuel cell. Uh, Taking one step further with fuel cell, doing a system level analysis. So this is another example of integrating a component level analysis with a system level analysis, where you have the fuel cell stack reduced order model, which was generated it can be generated in ANSYS Fluent. So once you have run through different designs or different scenarios for your fuel cell, you can create a reduced order model out of it, and it will do it automatically for you. And then you can plug that into your 1D system level representation, and then run it for different scenarios, different conditions, and look at the performance of the entire system. So if you are looking at, or you would like to modify the existing combustor designs for different kinds of fuels, That's something we can again look at in very detailed analysis using very detailed fuel chemistry models that are available in ANSYS Fluent ChemKin package. So there is a comprehensive database of more than 65 fuel components, and this can be tweaked as needed as well. You can add your own chemistry, or can use one of the combination of existing models. So this has been validated for a variety of scenarios. Those validation comparisons are available as well, and just to capture the accurate fuel chemistry is something that's going to be very important when we are looking at these different SAVs and working on any design changes that needs to be done. So the performance, again, this is looking at the fuel chemistry itself, how those different fuel combinations are going to behave. And the similar set of methods can be used when you are combining, making where you are using two types of fuels, or just and or a jet fuel itself, or a renewable fuel, or plus jet fuel. Different combinations can be evaluated, and as you can see, different uh, the NOx emissions and the fuel chemistry, the burnt fuel chemistry for coming out of different kinds of fuels can be evaluated as well. So it's the same level of fidelity that can be used for designing, making changes to the combustion design itself, as well as looking at different kinds of fuels for aviation. So here you can see um, different simulation deviations for a targeted mixture fraction. So you are changing uh, the fraction here, and this is basically building a digital twin of your different kinds of fuels, and changing their uh, the the fraction, and then looking at how it will impact at different different operating conditions. What would be the pressure profile, what would be the flow rate, and so on for different mixing fraction. So this is all can be very product or asset specific, and it can also use some of the physical test data that's coming from the field. So this was again built in Twin Builder with a system level model. We are not seeing the system here, but we are just seeing the how when we change the mixture fraction, how it's changing the pressure at different locations in real time for this pump. So this is a slightly different application, but also relevant for studying at different kind of fuel options for aviation as well. So this is biofuel simulation, where you are looking at how these um, uh, algae exposure to sunlight can help in generating these biofuels. So you are capturing that entire process. So for example, you can set up a parametric workflow to optimize the placement of mixing elements for improved photosynthesis. So that's the process with, like, this is with hydrofoils and this is with flow rips. So different kind of um, uh, uh, structures or geometries that can be modeled for capturing this process. So this is something that can be modeled as well in a simulation environment, and the effect of using different kind of mixing elements can be studied. So another important aspect of designing these sustainable products is around manufacturing. And we would we've been all looking at various methods for additive manufacturing, and how it can not only save, not only make the product more strong and lightweight, but also save on the carbon footprint in manufacturing that product. So modeling that process will give you a very um, important insight in how the product would behave in field, and how the what the product strength would be, how it should be the how the support structure should be um, made when you are actually 3D printing the product. This can be simulated in a 3D printing software, where you are looking at the complete design for additive manufacturing workflow through your validation. So you are coming up with the optimized design first, and then you're simulating the process itself. Then you'll be looking at the material analysis, so microstructure analysis, and then part qualification and material management as well. So this can be done in a complete end-to-end material process manufacturing design for manufacturing platform. Okay, so just to summarize, these were some of the examples that I wanted to go over with you today. Of course, there are a lot more areas that where simulation can be used for towards sustainability, but what I would like to emphasize here is that simulation is not only impacting in the design phase, which is it mostly used for, but the entire product life cycle. We are looking at how the product is going to be maintained, how it's going to sustain in the field, and that's where simulation can also help. Uh, and as we looked at the different ways where you can model these technologies in simulation, it will help you expand the design space, and also reduce your physical prototyping and testing time and cost both. Uh, uh, with the cloud infrastructure, and also the high advancements in the methodologies for scaling these tools, we have been able to run it the even the very high fidelity combustion like runs in a very timely manner, scaled down the runtime quite considerably. If you look in the last 5 to 10 years, and now we are at a stage where we can actually uh, use simulation as a commodity. So we don't have to spend days and weeks, months for getting these high fidelity results. We can run a set of simulation on cloud or HPC, come up with a reduced order model, and then use it for further evaluation and analysis. So that entire process is condensed and is much more faster than what it used to be before. With the system level integration, we are able to incorporate the effect of a variety of parameters that was not possible before. So with the digital twin concept, and also with just the doing the simulation at a system and system level, we are not only able to impact the design stage of the product, as but the maintenance and overall operational stage of the product as well. So with that, I'll stop here. I also have few references, and these I will share after the presentation. Um, so where you can go and look at some specific use cases for designing these sustainable products. There is also a recent award that we are going to be where we are going to partner with UCF uh, uh, for NASA, like University Leadership Initiative, on developing emission-free jet fuel and airplane engine. It's a design that we had proposed with UCF and University of Central Florida, and that was just got awarded last month. So that's something we are really excited about as well, among other uh, several other engagements that we have both with industry and academia in this space. So with that, thank you for your time, and I can take few questions now.
Great, Dr. Saxena, wonderful talk. Can you hear me?
Yes, I can hear
Yes,
you.
yeah. I think first, Dr. Marty Brady has a question. I try to ask them to share their camera, but looks like they prefer to stay just. So Dr. Brady, go ahead.
Oh, okay. I see you've unmuted me. All right. My question had to do with, you showed a really neat schematic of the hydrogen propulsion system.
Mm-hmm.
Are you familiar with the details of that work? Because I have a detailed question as to what the I get. I go back.
Is this one or the
Slide
design or
23, actually. Go to slide
23? Okay.
23. Yeah.
Yeah.
My question was, what is the function of the water, the H2O,
This
in
H2O
that
pump.
system? Yeah, and what does that do overall? Because I guess I wasn't familiar with using that
Okay.
with the fuel.
Okay. That's something, my guess is that it might be getting used for some kind of cooling, if I'm not wrong, but I'll have to look into that. Sorry, I'm not very familiar with the detailed uh, system here. I can get back to you on that if you're interested.
I was just curious. I wanted also,
Yeah.
I made a couple of comments. I was really interested to see that you had the slide 27 on the tanks,
Yeah.
because that's a really important area to get
Mm-hmm.
the design, and the pumps on slide 28. So thanks for that. And then I did put in a congratulations that you won that ULI for NASA. There was a lot of competition for that. I was on at least one of the losing teams, so congratulations on that.
Oh, thank you. Thank you so much. Yeah, we are I think one of the 4 teams that they awarded last December. So yeah, really excited to be working on that. There is a supercritical CO2 um, cycle that is that we have proposed as part of the system as well. So uh, I've worked on that before, so that's something that I'm looking forward to.
Okay, and thanks for the presentation.
Thank you, Marty. And I have noted down the question. I'll definitely follow up. I know the engineer, my colleague who had put together this workflow. So I will check with him, and I can send a note to Ken, who should be able to reach back to you.
Okay, thank you.
Okay, Dr. Jackson, Charlie Jackson, Dr. Jackson, go ahead.
Hi, this is Charlie Jackson. I'm more used to ANSYS products for electromagnetic simulation, so I was really pleasantly surprised to see how many other sorts of simulations ANSYS can do. Can ANSYS tools be used to reduce aircraft noise, or is reduced noise just an outcome of higher efficiency?
ANSYS tools can be used to model different sources of noise. One of them could be, just the aeroacoustics noise. If we are looking at the rotorcraft noise, or the noise generated because of the wing pylon interaction, so installation noise. So so basically, if we are able to simulate the complex flow uh, around different components, the interactions, as well. So both aeroacoustics and also vibration noise. So vibroacoustics noise because of the vibration in the structure that can be predicted as well. So if that helps.
That's interesting. Thank you. And then the other question is, can ANSYS tools simulate electric propulsion for satellites? It's not really an aviation application, but it does relate to satellites.
Yes, for sure. And I did not include those examples today, but we are working with for like space applications as well, and looking at different methods on simulating the for space propulsion and space uh, uh, yeah, other even the electromagnetic applications as well, especially on so for example, and this is a bit unrelated, but just would like to mention here that uh, for space as satellite applications, there are uh, new semiconductor devices or ICs that are being developed for that can operate at very, very low temperatures and so on. So those are some of the simulations that we can do uh, in ANSYS as well.
Aha. Well, that's all interesting. Again, I hadn't expected that ANSYS tools could help make carbon neutral fuels on one hand, and on the other hand, I expected they could improve efficiency, but all those things can really reduce carbon emissions or the carbon footprint of aviation. Thank you.
Sure, thank you.
So anyone want to ask a question? Uh, I think there's a gentleman, I think, commented on that. Albert, do you want to say something? I saw Vitali. You are welcome to speak out. But Albert, go ahead if you want.
Can you hear me all right?
Hello?
Can you hear me, Ken?
Yes, go ahead.
Okay. So, hi, Dr. Saxena. You presented information on fuel cells, but the slides were going too fast for me to follow. What is, in your opinion, what is the status potential of using fuel cells on aircraft?
Yeah, sure. So, I would not make a expert comment here because this is not my area of expertise, especially fuel cells. But I'm aware of some studies that people are, some options that people are looking at for using hydrogen fuel cell. They have been explored quite a bit for automotive applications, as you know. Uh, the what I was trying to show here was the possibility of simulating these kind of uh, geometries and mechanisms in ANSYS tools. So I will and I'll not make a expert comment on its application in aviation. I know there have been some initial investigations that are being done.
You mentioned in automotive, in the 1990s, there was a huge program to use fuel cells and hydrogen on cars.
Mm-hmm.
I think the initial investment was $1 billion from the US government. And that program went nowhere. And of course, batteries got so much better and took over. And I kind of, learning from that experience, I caution people pushing fuel cells too much on aircraft where the conditions are even more complex than automobiles.
Yeah, you're right. And I've heard about those challenges and constraints as well. No, I haven't done a extensive study on this, but those I think people are again looking at these options, but they're depending on how the integration and the overall system level performance can be estimated, it would, and of course safety is also an very important factor here for aviation.
Anyone else would like to comment on that from the audience?
Yeah, I would be interested in hearing if you have any comments on that. It would be good to know.
Yes, anyone, please raise hand. Oh, I see somebody raise hand. Oh gosh, okay, 1 second. Oh gosh, go ahead.
Yeah, very nice, excellent talk. I was wondering if you can do wingtip vortices also. Simulation of wingtip.
Yeah, sure. So actually, yeah, we have we can do it in Fluent. I don't know if you are familiar with the CFD software, but that's what we can use to model wingtip vortices, and it would be a high fidelity CFD run with to model the shear layer and the flow separation and the but it would be like that's where we can set up a 3D flow analysis for that. And any specific reason you would be interested in modeling that?
No, I used to one time.
Okay. Okay.
Thank you.
Actually, Dr. Saxena, I have a similar question like Dr. Charlie Jackson about the noise. And he was asking about if the noise simulation was by reduction of efficiency. For me, my question was the noise, can you simulate the noise kind of away from the aircraft, like in an airport, nearby situation, can you simulate the noise that can be heard nearby airport? And my second question was how easy it is to use a package, to set up the package to do all those great things you just showed. It's very expensive, and is this on a personal computer or require some kind of computer power?
So you are asking about the noise that is a far field noise, basically, right? So if you have a aircraft landing or taking off, what would be
airport noise is very
airport
important.
Noise, right? Yeah,
it's very important issue, and that's
yes.
part of the reason, big reason for sustainable aviation. That's a very important point.
Yes, absolutely.
Any directional, noise, certain direction, or distribution, something like that.
Yes, so it's actually a good question, and we can I'll send you some for some links about that later, Ken, as well. There is we can do it in two ways. So of course the high fidelity method that I was talking about earlier for doing the detailed aeroacoustic simulations, that will be very expensive. What we can do is do a far field or noise propagation estimation or prediction with one of the ANSYS tools, and can come up with the acoustic envelope. So that will be your signature for, if you are looking at a certain distance from the aircraft and around the airport region, that will give you envelope of the just the decibel level that aircraft would produce at a certain location or at the airport. So that can be done in more, let's say, just by using a propagation algorithm, we'll not be doing the high fidelity simulation for the entire region. That would be done for a very localized uh, the major sources of noise that are in an aircraft. So the rotor noise is the main one, and then if there is going to be landing gear noise, that's going to contribute, or the engine noise itself. So those components, and then use uh, a propagation kind of method to get your noise signature at a certain distance. So this can be done in ANSYS. There is a tool called ANSYS Sound VRX, and I'll send you more details later, that can give you that environment noise envelope when coupled with these uh, when you already have a noise source well defined, and can create a noise signature out of it. It can tell you what the noise profile would look like at a certain distance.
Yeah, that's great. Thank you. Actually, I have a second question, but Writer Lee has a question, so go ahead. I'll repeat my question again after him. I try to unmute him, but he may not be speaking out. Did you see his question in the chat? He said about the detonation combustion at m equals 4 on different fuel components.
Okay, I'm looking at it right now. Detonation combustion. Yes, so there is, I think I had a slide on RDE, which I didn't talk about. So if you see that slide now, this is the example. If you are able to see this animation, this is the hydrogen RDE modeling. So yeah, we do have few examples for this kind of simulation. I'll have to check the exact Mach number that it was run at, but that's it's something, yeah, definitely that we have looked at.
Ask a question related to that. Can you hear me all right?
Yeah, I can hear you now. Yeah.
Albert Musa here. That model, as I see it,
Yeah.
assumes detonation will happen, and then you're looking at the gas dynamics
Yeah.
produced
Yeah.
by it. But the question is, can you predict detonation?
Okay, so my guess, or if I want to pick an educated guess here, it would be yes, because we are capturing the chemistry here. But I can get back to you on that specific question, and if we have done something like that, a use case, I can also point you to that.
Thank you.
Thank you. Thank you for question.
Yes, Dr. Saxena, actually, my second question earlier was that for those simulations, you just mentioned the hydrogen fuel, those things, do they require special computer power? Is a personal computer or need like a cloud-based computer on an ANSYS server or?
Oh, okay. Sorry, I missed out on that part of the question. Yeah. So there are several options available. ANSYS Cloud is an option as well, where you can use our cloud infrastructure to run your simulations. We also partner with other public cloud vendors, and also like Azure and AWS. We can also deploy the ANSYS tools on your own private cloud. So all those options are there. It can be on a small cluster as well. If it's not, it doesn't have to be too big. So private cloud, public cloud, ANSYS cloud, and then on-prem HPC clusters, those all those options are possible.
You mentioned HPC. That's actually I was about to ask that. But if it's on a personal computer, is there any memory or CPU minimum requirements?
Yes, there are requirements, and depending on the simulation that you are that you would like to set up, and we also give some recommendations on using the RAM, the minimum amount of RAM that you should have, and also the processor type, GPU requirements as well for post processing. So actually, let me note it down. There is a platform recommendation or requirements page that you can look at if you for every like individual ANSYS tool for both Windows and on the Linux system. That I'll send you that link, so you can see the list of recommended and kind of approved, validated uh, uh, processors and operating systems there.
Yeah, you mentioned Rolls-Royce, in some of your slides.
Yes.
And they have been doing a very good job. And I'm wondering, did they use ANSYS?
Yeah, so the example that I was showing, this is where they were using ANSYS. I think this was the slide. Yeah, and this was just a quote from them. So yeah, this for this particular analysis they had used ANSYS.
So maybe it's their company secret, but do you know, or you think in general that the company use ANSYS to prototype, or they actually has already built some kind of sustainable aircraft and just use ANSYS to verify some process or some design, or they heavily rely on ANSYS from the very beginning?
So yeah, it depends. Some of the customers like Rolls-Royce, they have it more embedded. So there is a more embedded in their design process. Some use it later in the design where they have already come up with their initial design, initial CAD, and then they will use ANSYS for a component level analysis. But others use ANSYS at an earlier stage as well. So for some initial design selections, design decisions, there is a set of design tools. You can look at ANSYS Discovery, which are more used by designers and not really analysts. So in this case, I think they are talking more about the high fidelity design optimization with adjoint methodology. So this will come a bit later once they have at least narrowed down on their initial selection. So in this case, they were using, I believe, ANSYS Fluent for this. But there are design tools, as I mentioned, like the ANSYS Discovery, that are used by some groups, if not all. So it depends on the team.
Yeah, I see. Yeah, because Rolls-Royce has a lot of good news recently, so kind of very good example. But I'm pretty sure there are actually other companies, working
Yes.
very. I think Zero Avia, also in the news.
Yes. Yes.
Any simulation kind of animation for those sustainable aircraft in the air? Can you simulate their performance in the air and compare with the regular engines?
So you're talking about at the overall, like the system level, or when you say performance, what are you kind of
Well, maybe
looking
like
at?
fuel efficiency,
Mm-hmm.
and when they fly in the air with air, resistance of the air,
Mm-hmm.
and that kind of situation with fuel efficiency, those only battery or how much they would need before refuel, and any different in aircraft performance, you know, uh,
Mm-hmm.
like structure wise, due to the difference, maybe, yeah.
Yeah. So something like this, right? I think you are talking about the different scenarios during which the flight would be for that entire flight envelope, right? If you are uh, taxiing in an all-electric fashion,
Something like
and
this with hydrogen or different things, biofuel.
yeah, so yeah, we can model that. So depending on the drivetrain or the propulsion system you are looking at, you can model it in a system levels kind of simulation, right? So something like this, and there you can look at the fuel efficiency and performance of different components for at different flight conditions. So that would take into account uh, your air resistance, in the sense what kind of pressure you have at the uh, for your system, inlet system, what kind of flow rate is going to be operating at. If it's operating at its 100% speed, or if it's in like idle condition, or if it's taxiing or climbing, it's climb, or and so on. So different um, operation cycles for your propulsion system. um, it can simulate that in this manner, and then you can uh, evaluate like different propulsion systems and look at the overall efficiency of your system.
Yeah, Dr. Bradley is not as lab, but otherwise he could tell us, because this sustainable aviation is related to the green aviation. There's
Yeah,
supposed to be quite some advantage, from the urban area,
yeah,
quiet,
yeah,
fuel efficient. So there are a lot of aspects.
right.
Simulation will be very helpful.
Yeah,
For
yeah.
this.
Yeah, especially for this urban air mobility, you have to look at all these. It's going to fly low, and it's going to. You have to really optimize the trajectory. You have to optimize the propulsion performance, so that you are um, able to maximize its uh, the duration of your flight, its flight envelope, and so on. So this becomes very important.
Yeah, just to comment on Dr. Charlie Jackson's question about the electric propulsion for satellite. Um,
Yeah.
yeah, I think he's been thinking about simulation for the propulsion, but actually the electric propulsion is related to plasma physics. Which ANSYS capable of doing plasma simulation, plasma physics simulation, have this kind of physics model.
So plasma modeling is, yeah, um, that's something that we can do in Fluent, and it has been extensively looked at for you know um rocket propulsion, and for satellite propulsion as well. Specific, actually, let me note it down. Can
That
send.
actually could be a very good topic for your
Yeah.
next talk, actually.
Yeah, okay, I'll see if I can put something, like I can, if I have like enough enough material for that. But this is of course a very important topic. I think we were also discussing about hypersonics in one of our previous talks, and that's where the plasma modeling, ablation, and all those phenomena become very important.
Yeah, exactly. Yeah,
Yeah.
very interesting.
Okay.
Right. Fantastic. Any more questions from the audience? Yeah, this is really wonderful talk, a very hot topic and a great speaker. So thank you very much for joining us. The link of the recording and podcast will be emailed to all the registrants and attendees today, this evening, or tomorrow. So look into your email or check the spam or junk folder, and it will be also posted on the weekly, Monday weekly event summary email. So, okay, thank you very much. So we have another wonderful talk. Look forward to Dr. Saxena's next talk with us. And,
Thank you.
Yeah, thank you so much.
Thank you so much, Ken, for the opportunity. Thank you. Take care, everyone. Okay.
That's wonderful. Okay, folks, yeah, look forward to seeing you on February 19th and February 23rd. Stay in touch and enjoy the rest of the beautiful Saturday and enjoy the weekend. Thank you so much. Bye-bye.
Thank you. Bye-bye.
Beautiful. Thank you very much.